Hello, welcome to part 3 in our mini-series on measurement-based quantum computation. Part 3 today is on measurement-based quantum computation with probabilistic, heralded entangling gates. And despite the considerable length of the title, the lecture itself will be rather short. There is a single idea to convey. However, this idea will have profound implications for the physical realization of quantum computation. To begin, let us review what we learned in the first 2 lectures. So the central object of our discussion is the two-dimensional cluster state, which is a computational universal material, it turns out. Information is written onto the cluster, processed on the cluster, and read out from it by 1 qubit measurements only. No unitary evolution ever takes place in the process of computation. Everything is done by local projective measurements. And now we come to the subject of today's lecture, measurement-based quantum computation with probabilistic heralded gates. Probabilistic is not good, so this means that these gates sometimes succeed and sometimes fail. Heralded is good. This means that whenever the gate succeeds, we learn that, and when the gate fails, we learn that too. Let us first discuss what the problem with probabilistic gates is. In a quantum circuit, you typically require every single gate to succeed. Just a single gate failing can lead, or typically will lead, to failure of the entire circuit. This means that the overall success probability of the entire circuit is exponentially small in the circuit size. So this is the problem that we have to face here. And a simple solution to this problem would be to just ignore this extra information of whether the gate has succeeded or failed and recur to standard techniques of quantum error correction. That is perfectly fine. However, it works only when the gate success probability is very high, say 99% or higher. It turns out, though, that one can do much better if one pays attention to this extra information, whether the gate has succeeded or failed. Then it turns out that one can get by with much lower success probabilities of the gates. In fact, one can get by with any non-zero success probability. And that is the subject of the lecture today. And this slide gives you an overview of the idea. Before I begin to explain this idea, let me just mention a major application of all of this. So the techniques that we are going to discuss today, they are very useful in reducing the overhead of the KLM scheme of linear optics quantum computation. KLM is after the inventors Knill, Laflamme, and Milburn. So if you ever have the idea of doing quantum computation with photons, the cluster state approach helps you enormously with keeping comparatively low the amount of resources you need. So now let's see why this is so. And this is shown for the one-dimensional case, for the case of one-dimensional cluster state in this picture. Higher dimensions are just straightforward generalizations of the ideas that we present here. So let's go. So what we see here is a one-dimensional cluster state. And on the right-hand side, this cluster state is continuously extended by conditional phase gates. And on the other side, the cluster state is shortened by the measurements that drive the computation. So now the particularity of the situation is that these entangling gates are probabilistic heralded. And so this means they do not always succeed, but on average they succeed, and on average this chain gets longer and longer. So it is on average appended to, on the right hand side, while at the same time it is shortened at the left-hand side. So now, the extension and contraction of the cluster chain on the right is a probabilistic process, so there's fluctuations. And so you need a safety distance between the left and the right to buffer these fluctuations, so that the cluster chain never becomes so short that it interferes with the measurements on the left-hand side. So this is the basic idea. In this way, quantum computation with probabilistic heralded gates becomes very efficient. And the purpose of today's lecture is to talk about that in some detail. Okay, so there's really just two ideas that enter here. It's very simple ideas. So fact number one is that a cluster state can be appended to by applying conditional phase gates. This relates to the scenario that we described earlier. The cluster states can be created by the Ising interaction, and conditional phase gates are just the computer science version of applying the Ising interaction. These conditional phase gates pairwise commute, and so they can be applied simultaneously, but they can also be applied one after the other. So I can make a cluster state 1 qubit larger by applying one conditional phase gate. And so this is what we see here in the upper half of the slide. We perform one conditional phase gate on an extra qubit in a sigma x eigenstate and thereby extend the cluster by 1 qubit. So this is fact number one that we are going to use. So this is for successful creation of cluster states. So the second fact has to do with what we do when those gates fail, which sometimes happens. And I remind you here of one of the steps of the universality proofs. Step 4. Therein we showed that if we have a cluster chain and measure one of the qubits in the eigenbasis of sigma z, the effect of that is to remove that qubit from the cluster. Okay. So these are the two ideas that we are going to use, and next is how to use them. So here we see a situation that might occur. So this is the cluster chain that already existed, and now we attempt to add another cluster qubit to it by applying a conditional phase gate. And if that conditional phase gate succeeds, fine, then we have extended the cluster. But if it fails, then what? So the good thing is that whenever it fails, it tells us so. And then what we do is we measure the cluster qubit to the left of it in the sigma z basis. And the effect of that will be that we are losing the qubit that has been measured, we are losing the stuff to the right, but we remain with the cluster that existed to the left. So in effect, the cluster chain is shrunk by 2 qubits. So we wanted to attach one, but that failed. Namely, we are losing this qubit and the qubit to its left, but the chain farther to the left remains intact. So why is this so? So the reason is, think of the temporal order of these operations. You have a failed gate applied first, and then a z measurement second. But because these two operations act on different qubits, they commute. And you might alternatively think of the operation as the z measurement performed first and the failed gate acting second. And if you think about it that way, it's clear what happens. So the measurement of sigma z splits the cluster in two. So the left and the right become disentangled. And now what subsequently happens to the right part of the cluster will not affect the left part of it. So this is the explanation, and let's now analyze the consequences. There's two cases to analyze. A, the cluster extension succeeds, the conditional phase gate is successful, and in this case the cluster chain length is increased by 1. In case of failure, the cluster chain length is reduced by 2. And so the expected change in the length per time step is the following. If we succeed, we increase the length by 1. If we fail, we reduce the length by 2. And that works out to this expression. So the expected change is 3 times the success probability minus 2. And so, if the success probability is larger than 2/3, then the cluster grows on average, and we are fine. Okay, so we can now understand this picture in greater detail. So this is the extension of the cluster state. Suppose our success probability is larger than 2/3, so on average we gain with a certain speed, and we can measure on the other end, but we have to keep a safety distance just to buffer fluctuations. A question that comes up immediately at this point, I suppose, is what shall we do when the success probability is smaller than 2/3? Well, that's your homework assignment. So let me just wake your appetite a little bit. You might come up with a construction that is efficient in the cluster size for any fixed non-zero success probability. This is the end of the lecture. Let me summarize. What we discussed today was how to compute with probabilistic but heralded entangling gates. We have seen that the model of measurement-based quantum computation with cluster states is very helpful for that purpose. It tremendously reduces your resource requirements. I have shown this to you only in a special instance. For example, I didn't tell you what to do if the success probability of your entangling gate is below 2/3, and I didn't tell you what to do when you wanted to create a 2-dimensional or 3-dimensional cluster state, but these are details. These are now straightforward extensions that you can figure out. These techniques are particularly relevant in the context of quantum computation with photons. So the KLM scheme of linear optics quantum computation in particular is made orders of magnitude more efficient using these techniques. Let me conclude with a couple of reading suggestions. So, from the physical perspective, as I just pointed out, this is most useful for the KLM scheme of linear optics quantum computation. And so here is that paper useful as background for the present constructions. Then, the techniques that I reviewed today in this lecture, they are mostly from those two papers by Mike Nearson and by Dan Brown and Terry Rudolph. So there's orders of magnitude more papers on this very subject, but I think this gives you a starting point. I would also like to direct you to this recent review article by Terry Rudolph, where he discusses the idea of quantum computation with photons in general. So thank you very much for your attention. That is all for today.